In remote drone piloting, pilots can only see this kind of FPV from the drone's onboard camera. But, as shown in this third-person view, the pilots suffer from a range of blind spots because the FPV captures only the limited frontal area. Even if such TPVs are available in remote piloting, pilots cannot exactly understand the main drone's spatial status such as height and distance to the object because the depth cues are limited. We propose BirdViewAR using two drones, where the follower drone is flying behind the main drone at a higher altitude, to offer a bird's eye TPV. The follower drone position and angle are automatically controlled to respond to the main drone motion and maintain an effective TPV. Additionally, the TPV is visually augmented that helps understand the spatial relationships between the main drone and its surroundings. Here, we explain the details of each augmentation. We introduce an optimization process to produce motion-dependent automatic TPV control which offers a wider area of the current motion direction in a stable way. When the main drone moves to the backward direction, the follower drone's camera tilt and altitude are changed to capture the main drone as well as its 1.5 seconds future destination. We designed 4 types of AR overlays. We highlight the drone's head angle by a triangular overlay, which helps pilots to quickly understand the direction that the drone is currently heading. A height bar overlay visualizes the altitude and ground position of the main drone, which helps manipulations such as passing over obstacles and landing to the specific position. We add circular distance guides, allowing the pilots to always grasp the drone to subject safety distance in all directions. FPV frustum visualizes the main drone camera's FOV. The frustum's bottom edge and TPV corresponds to the actual FPV's one, allowing for a rough camera framing. We implemented BirdViewAR using 2 programmable drones. In our system, the pilot can see both TPV and FPV with 2 monitors. When the main drone goes right, the TPV's captured area changes. When the main drone goes upward, the TPV moves to contain the FPV frustum. We conducted 2 tasks in our outdoor experiment, nose in circle and fast positioning tasks. At the nose in circle task, in FPV only, it is difficult to grasp the distance between the target and the main drone. By plain TPV, pilots can perceive objects in the environment, but it is difficult to grasp the exact spatial relationship around the main drone. Our AR visualization assists the pilot's clear understanding of the spatial status of the main drone relative to the target. At the fast positioning task, in FPV, pilot cannot see motion direction, so it is difficult to position at the target location precisely. In top view AR, it might be not easy to recognize the target, making many overshooting. BirdViewAR's motion-dependent TPV helps the pilot's prediction and enable precise online path planning. We show the application scenarios of BirdViewAR. A small display is mounted on the main drone. When a security officer finds an outsider in the FPV, and this officer can manipulate the flying display close to the outsider using TPV. The officer can adjust its altitude to the outsider's eye height and safely approaches it to his view area. Another example is videography. 2 circles in the TPV visualizes an ideal range of safely capturing the moving subject. Even if the subject turns to a different direction, suddenly a videographer can capture the target and understand the spatial relationship between the camera drone and an obstacle, so that the pilot can avoid the obstacles and modify the motion path real-time.